All right, physicists, welcome to our January 27th edition of Physics. Big day for physics today. We're going to take our leap into the second dimension even farther. So today it's the day where we do one of our first big physics steps where we're going to do projectile motion problems. Never fear, every step is a small step. And if it's confusing, we'll try to go over it many times. Okay, so what did we do last time? Last time we talked about vectors and scalars. Now, if we have a non-directional quantity, by non-directional, I mean it doesn't have a pointer attached to it. We describe that with a scalar. So an example would be something like temperature or just distance. If we didn't care about the displacement and only wanted to know how far, we could use that as a scalar quantity. On the other hand, if we have a direction associated with it, if it could be positive or negative, if it has a pointer, we would use a vector. And so examples of that would be things like not just distance but displacement, or not just speed but velocity, or things like direction of water flow, or anything like that could be described by vectors. Now, as we said, this vector is a pointer, and if you want to describe that pointer in a sort of a slick way, you can always resolve it into its components and describe it as the sum of two pointers. There's one pointer in the x direction plus a pointer in the y direction. And if you want to add those two together, they give you that final vector. And if you want to add two vectors together, it can be done by resolving them into the components, x and y parts, and then adding all the x parts together, and then adding all the y parts together. So, for instance, here is my a plus b. If I were going to draw that a as one vector and draw b as a different vector like this, my a would have an ax and an ay component. My b, there's my vector a, my vector b would have a bx and a by component. That would be a negative number. And then if I wanted to find my a plus b, well, I could do that by having ax plus bx times I. I is now our notation for a unit vector in the x direction, plus ay plus by times j hat. And that j hat is the notation for a unit vector in the y direction. And geometrically, when adding those two vectors together, it means that you're taking the first vector, so there's a, and then putting b on its tail, and then when you add them together, it gives you a plus b. So that would be ax plus bx would give you this, and then these ay and by. In this particular picture, they are matched up, positive and negative, so the component of the final vector in the y direction is 0. Okay, so here's a homework problem that I gave you on resolving components. It says, what are the x and y component of a vector in the xy plane if its direction is 250 degrees counterclockwise from the positive x direction? So there's your plus x direction. There's your plus y direction. Here's your minus x and minus y. At 250 degrees, well, if I'm looking here, here's 0 degrees, 90 degrees, 180, 270. 250 has to be somewhere around there. In fact, if this one is 270, I guess that would have to be 20 degrees, and this one would have to be 70 degrees. Okay, and it asks, find the x and y components. Well, as I told you last time, if you want to do this, you can simply write out your components. So, for instance, this would be and my x direction and my y direction would just be 7.3 times cosine of 250 and 7.3 times sine of 250. And the nice thing about this particular notation is that it already takes care of your sines for you. So just looking at this picture, you can tell that this vector is going to have a negative x component and a negative y component because it's over here in the third quadrant. But this takes care of that for you. On the other hand, if you wanted to do this with trigonometry and just split this up into a, an x and a y component, that would be perfectly fine to do. Okay, so I think it's good to have a little bit of flexibility in your thinking and just not just be plugging things into equations. Okay, here's another one that I gave you for homework. It says, in unit vector notation, what is the sum a plus b if a is that and b is that? What are the magnitude and direction of a plus b? Well, I'm not afraid to do this for you because I think this part is pretty easy. I told you if you want the x component, you just add together the two x components. So 4 plus minus 13 is minus 9.0i. And then 3 plus 7 is going to be plus 10.0j. Okay, so if I draw that out, that's going to be minus, here's your x direction, there's your y direction. That's going to be minus 9 over here, so 9 behind the origin in the x direction, and then plus 10j, 10 meters there, 9 meters there, and there's our final vector. All right, now for finding the magnitude, you're just going to use your Pythagorean theorem, so that's no problem. I will say for the finding the angle thing, you do need to be a little bit careful because if you just mindlessly use this formula, it will always give you an answer that's between minus pi over 2 and pi over 2, or minus 90 and 90, depending on what units you have on your calculator. And so here's a triangle with 10 on one side and 9 on the other side. And if you wanted to find that angle, you could always use inverse tangent of opposite over adjacent, so 10 over 9. That would give me this angle right there. And then if you wanted to find the direction in terms of the usual way of labeling this, the direction would be 180 minus that angle. Okay, so just be aware, even though the equations are set up pretty slickly, you don't want to just apply them mindlessly. You always want to think carefully about what you're doing. Okay, so today, as I said, we're going to rush forward into two-dimensional projectiles. So I think it's useful before we do that just to make sure we're absolutely clear about how to do problems with one-dimensional projectiles. So remember, this is our picture. Now for forevermore, unless told differently, we're always going to assume that gravitational acceleration near the Earth is 9.8 meters per second per second. And let's look at this problem. Tommy stands at the end of a dock that is 2 meters above the sea. So I'm going to draw a picture. 2 meters up, and there's the ocean. He throws a firecracker straight up at 8 meters per second. 8 meters per second. Immediately after lighting it. This type of firecracker is known to explode 3 seconds after being lit. will it go off before hitting the water? Interesting problem. So this is essentially one-dimensional motion. The firecracker is just going up and down. You know that we're going to be interested in where the firecracker is at time equals 3 seconds. This is where we are at time equals 0 seconds. And let's put some numbers on here. For convenience, you just need to label the origin somewhere. So let's make this 0 meters. And then that would be 2 meters on our number line in the y direction. And if we're going to use our accelerated motion model, what we want to do is to figure out where that firecracker is going to be at 3 seconds. So let's see, what do we have? We have y minus y naught equals v naught in the y direction times t plus 1/2 at squared. Okay, so if we wanted to find out what is the y at time t, we would have to use y naught. That's the position in y at time equals 0. So that would be 2 meters. Plus v naught y times t. Well, our v naught y, it's going up in the at 8 meters per second at the very beginning. And as it goes up, it slows down, and then it turns around and begins falling back down towards the water. And that's going to happen at time equals 3 seconds is the time that we want to find out our final position at, plus 1/2 acceleration times t squared. So the time in both cases is going to be the same. Notice here we're going to use 3 seconds. Here we're going to use 9 seconds squared because it's t squared. And our acceleration in this case would be minus 9.8 meters per second squared. Why is it going to be minus? Well, because the acceleration is downwards. Okay, so the acceleration sort of does have a direction in this case, because if we put in a positive acceleration, it would mean that our ball was getting faster as it goes up. And we know that's not the case. Okay, so just plug in all those numbers, find out if y is positive or negative, and you would have your answer. I don't really care what the answer is. This is not a homework problem. It's an example problem. Okay, now I want us to think clearly about how we're going to deal with these ideas of initial velocity in 2 dimensions. Okay, so that last problem, we used an initial velocity of the firecracker, but it was only in one direction. Now, here's just a picture that I've cooked up for you. Now, suppose that we have a walker who's walking across a food court at a mall, and there are these grids on each side that are 1 meter by 1 meter. Okay, and this person, I guess it's a not very busy day at the mall, and is walking across at 5 meters per second. Okay, so this person is going 5 meters, and then after 1 second, 10 meters after 2 seconds, 15 meters after 3 seconds, and essentially we can represent that very easily. It's just a constant velocity motion. X is going to be 5 meters per second times time in seconds. Now, if I just look at this graph, there's an interesting fact that I'm not going 5 meters per second in the x direction or in the y direction. If I just wanted to represent where the x coordinate of that motion is, you notice after 1 second he's gone 3 meters, After 2 seconds, this person has gone 6 meters. After 3 seconds, they've gone 9 meters. So in the x direction of this particular choice of coordinates, my x position would be 3 meters per second times time. And then my y direction, I'm moving 4 meters per second, 4, 8, 12. So I would have that this would be a possible way of writing it. So in one way of writing the coordinates, this is one-dimensional motion. In another way of putting it, this is two-dimensional motion. Okay, so I haven't done anything tricky here. I've just represented the way of writing that in two different ways. However, this should make me think that if I'm going to use coordinates like that and I want to split up the velocity, okay, I can do that using trig. And how does it work? Well, velocity looks like a vector. Okay, so here I have my initial velocity that is not changing in this problem times time. And if I wanted to find my initial velocity in the x direction, I would use that initial velocity, the magnitude times cosine of theta. And if I wanted the initial velocity in the y direction, it would be the velocity times sine of theta. Okay, so that's exactly what I did in the last problem with a 3, 4, 5 triangle. That was just a more concrete example. So essentially, that's what we're going to do today. We're going to have, for a projectile, you throw it. It has an initial velocity in the x direction, an initial velocity in the y direction that you get from using the angle and splitting up your initial velocity. So why is it any harder than that? Well, the only reason it's a little bit harder is that we're going to have to mix our models. When we split up our projectile motion into two dimensions, we have accelerated motion in one direction. That's in the y direction where our ball is falling. And we have unaccelerated motion where we have constant velocity in the x direction. So if you're looking at this red ball, this is a picture, a time-lapse picture where each dot represents the same amount of time. I can see that this is not moving along the y direction, but every second I'm moving farther in the y direction. So that is accelerated motion. So I'm going to have to use my accelerated motion model in the y direction. And in this, in the case of the red ball, my x direction is just staying constant. So I would just say x is some constant value. On the other hand, for the y ball, I want you to notice that the ball is lining up every time with the red and the yellow. The position at subsequent times is the same in the y direction, but when I've thrown that ball out horizontally, essentially what's happening is that every second it's moving the same distance, or every unit in time, it's moving the same amount of distance in the x direction, but it's moving a bigger amount of distance in the y direction. So it starts out moving not very much, and it's moving more and more and more and more. Okay, so the key idea of today is that for these types of projectile motion problems, we're going to have to use constant velocity motion in the x direction and accelerated motion in the y direction, and together those tell us everything we need to know about the position versus time and velocity versus time of the ball. Okay, so that's the basic idea. To get there, let's take a step back. Okay, so we have already gotten pretty comfortable describing things in terms of vector, or in terms of position and displacement and all that in one dimension. Everything that we've said about one dimension carries over to 3 dimensions or 2 dimensions if we use vectors. So for instance, if we go and we just had our position in x that was along a number line, we can now have a vector for position with x, y, and z. And if we had our displacement, which was our final position minus our initial position, well, before we were doing that just in one dimension, so we had our final position in x minus our initial position in x, but we can also do that in 3 dimensions. Final position in x minus my initial position in x, that would give us our displacement in x, delta x times I hat, this is a vector now, plus delta y times j hat plus delta z times k hat. So now I have, instead of just a displacement that has a sign, it's a plus or minus number, I'm going to have a plus or minus number for each of my spatial dimensions. So plus or minus number for x, plus or minus number for y, plus or minus number for z. Okay, so in principle, everything that we've said about position versus time stuff in 1 dimension carries over to 3 dimensions pretty easily. So there's a nice example in your book where they describe the position of a rabbit in x and y versus time. So here's the equation for the x coordinate. There's an equation for the y coordinate. If you put in, for instance, x time equals 0, the x would start out at 28 meters. If you put in time equals 0, the y would start out at 30 meters. That's this point right here. And as you go forward, the rabbit has a position at every time in the future, and it follows this path right here shown in the picture. Now, the rabbit's velocity is going to always be some number based, and its direction is going to be tangent to this curve. Okay? Now, how do you find that velocity? Well, everything that, as I said, carries over. So to get my Vx, I could just use dx dt, take the time derivative. Velocity is how the position is changing in time. And so in that, just taking that derivative, it would be minus 0.62 t plus 7.2, and then that would be just 7.2, and then that would not contribute because that's a constant. And then Vy would be dy dt equals 0.44 t minus 9.1. Okay, so you can find out what your velocity in the x is at any point in the future t, and what velocity in the y is at any future point of t. And if you wanted to find out what the speed was, you could just use your Pythagorean theorem there. Vx squared plus Vy squared, because that v at every point would be a vector. So I gave you a couple homeworks like this. In this one, for instance, it says a particle moves so that its position in meters is a function of time, is something, write expressions for its velocity and its acceleration as functions of time. Okay, so for instance, if we wanted the velocity as a function of time, our r is I plus 4t squared times j plus t times k. And if I wanted to take the d dt of that r, well, I is not a function of time, so the derivative of a constant would just be 0. And then this would be plus 8t times j plus k. Okay, and then you take another derivative of, and that would give you your velocity as a function of time. Okay, and then if you wanted to find your acceleration, you just do that again. Take the derivative of this expression. All right, so I gave you a couple of practice problems like that. And just as with our instantaneous velocity and acceleration, our average velocity and acceleration also carries over into 3 dimensions. So for instance, if I have a displacement over a total time, I can find my average velocity, and if I have my final velocity and my initial velocity as vectors, I can take the difference in those and find an average acceleration if I divide by the time as well. Something to notice about this is that, as I said, your velocity, this line is representing the path of a particle in the xy plane. The position, the velocity at any point on that curve is tangent to the curve, right? But the thing to be careful about is that if you choose any 2 points on the curve, like this 1 and 2, you can always find the average velocity between them just by taking the difference in position. So this vector minus the xyz components of this vector minus the xyz components of that vector, and then divide them by the amount of time between the two positions. And that's all fine, but at many points between there, the instantaneous velocity is pointing in a different direction. So for instance, over here it's pointing like that, over there it's pointing like that. And so there's going to be one point between the two where the average velocity and the instantaneous velocity have the same direction. That's a calculus fact, but not at all points. Okay, so here's another sort of example on your homework, number 14 on the second page from chapter 4. It gives you a proton initially has some velocity, and then 4 seconds later it has some different velocity. For that 4 seconds, what are the proton's average acceleration in unit vector notation, the magnitude of that, and the angle between that and the positive x direction? Okay, so the delta v is going to be this last one minus the first one. Okay, so in the x direction, we end up at minus 2 x minus 4. Okay, so that's my change in velocity in the x direction. And then in the y direction, it's plus minus 2 minus a minus 2. So that's plus 2. And then in our k would be 5 minus 3. Okay, so our delta v then would be minus 6i plus 0j plus 2k. And then for our average acceleration, we would have to divide that by 4. So each one of those gets divided by 4 to get your average acceleration. I know from drawing this like the way that I have that in the I direction, here's your x direction, and this is going to be your z direction. In your y direction, it's not pointing in that. I would have something like this, minus 6, 2. Okay, so it's not going to be exactly that because it's going to be divided by 4. But that's the direction that your a average is going to be pointing. Okay, so be careful because when it asks for the direction, the angle between a average and the positive direction of the x-axis, well, you can find this angle here by using your inverse tangent, let's call this your AX and your AZ of your AZ over AX. And then if you wanted to find the angle right there, which is what they're asking you for, the angle between A average and the positive direction of the x-axis, well, in that case, that's going to be, so this is, let's call that, give that a prime, and then the angle that you're looking for is going to be 180 minus that primed angle. Or if you if you want to use radians, you could use pi minus that primed one. All right, so we've gotten past all the prologue now. Let's go ahead and look at how our projectile motion problems work. Okay, so to reiterate what we said, in our y direction, we're going to have accelerated motion. So that's my red arrow, my particle. This is representing the velocity of the particle. Essentially, that goes down to 0 at the top, the 0 velocity, because it's turning around in the y direction and it starts coming down. So we have accelerated motion in the y direction, constant velocity motion in the x direction. So let's see. I'm not going to fully solve this problem because you're going to see how the algebra gets a little tricky, but I want you to understand how this works. Okay, so here's the problem. It says an athlete kicks a field goal from 40 meters out. With the football starting its trajectory at an angle of 30 degrees. How fast must the football go at launch to clear the 3-meter high crossbar? Okay, so the ball is going to go like this. Maybe I should have it going higher. Here's your V. And then at the end of the field, this is 3 meters tall. That's where I need to end up. Okay, so essentially what we're doing here, we have part of that velocity, initial velocity, is going to be in the x direction, v naught x, which is going to be whatever v that is, times cosine of 30. And then, this is 40 meters. Okay, then our v naught y is going to be v naught times sine of 30. I don't know what the v naught is. In fact, that's what the question is asking me for. But you'll notice in the y direction, I have y equals, let me see. There might be a, yeah, no, I think I have to do it this way. I have y equals 1/2 a t squared plus v naught t plus y naught, but let's just pick our coordinates so that that's 0. So there's your y, and there's your x. And then I have my x equals v naught, and let me make sure that I'm being clear here. This is v naught in the y direction times t. And then here I have my final position is v naught x times t. Okay? Now, how would I solve this problem? Well, what I would do essentially is the following. What do I know? What do I need to know? I know my final y has to be 3 meters. That's this position in the y direction. I know my final x has to be 40 meters. Don't know this. Also, don't really know this, but I know it in terms of v naught. Okay, so this is going to be v naught cosine 30 degrees. This is going to be question mark. Don't know this. I know that this has to be V naught sine of 30 degrees. And my A in this case is my gravitational acceleration, so it's going to be my minus 9.8 meters per second squared. Okay, so how would I solve this problem? Well, here's how I would do it. I would go ahead and solve this second equation for t, then stick that t into this equation, and at that point, I would have an equation that simply has v in it and everything else I know. So then I could solve the problem. Now you might say to yourself, geez, that's a terrible problem. That's quite complicated. And I say, okay, it's a little bit complicated, but it's definitely doable, and I don't think it's anything to be scared of. And if I give you a problem like that, I probably will give you a little bit more scaffolding. All right, so let's do a concept check. When it is at the top of its trajectory, what is the football's y direction velocity? Okay, so looking at it again, our velocity in the y direction is biggest at the bottom, it gets smaller. At the top, the y direction velocity is 0. Okay, at the same point, what is the y direction acceleration? Okay, not a trick question, but maybe a little tricky. The y direction acceleration is constant. We're using constant acceleration actually in both directions. In the y direction, it just happens to be negative 9.8 meters per second squared. In the x direction, the acceleration is 0. Okay, so that's something to keep in mind. An interesting theorem that you can prove using basically the setup that I showed you 2 slides ago is that a projectile launched at angle A will have the same range as one launched at angle 90 minus A. So here, for instance, at the shortest place, you have 15 degrees and 75 degrees. Notice those add up to 90. They have the same trajectory. They're not in the air the same amount of time. If you shoot at a low angle, you're in the air for less time. If you shoot it at the high angle, it goes way up and then comes way down. Okay, and then here we have, for instance, 30 degrees and 60 degrees. And then if I want to get my maximum range, I would go out at 45 degrees. Okay, so that's an interesting fun fact about projectiles. Now, obviously, I haven't included air resistance, so that makes a little bit of difference. But for a lot of these problems that we do in the lab, that doesn't actually matter much. Now, I want to show you there actually is another way that you could do the same problem that I showed you with the football, and that would be a case where you have a toy cannon, and it always shoots at the same speed at 4 meters per second, and you've got some distance to the edge of the table, 0.5 meters. And in this case, you're solving the problem where you start at an angle, you end at the end of the table, and it asks, what's the minimum angle between the barrel of the table that allows the pellet to reach the floor? Well, it's essentially the same as the football problem that I gave you before, except you're ending at the same height as you start out at, and the other thing is that you, instead of not knowing the initial speed, you don't know the initial angle. But here, I worked out this problem earlier and stuck it into just a plotter. And you notice that the lowest angle that you could go and solve this problem is 9.23 degrees. Anywhere where you're higher than that, and between that and 80.77 degrees, you're in the range where you would shoot the ball and it would just go off of the table. Notice that these are complementary angles. So in that case, you would go like that. So if you had smaller than this, your projectile won't make it past the table. If you go steeper than that, the ball also won't go past the table. All right, so that's an interesting problem. Now, just to hammer home these points, what angle of launch leads to the same projectile range as a launch range of 22? Okay, that would be 90 minus 22. So 90 minus 20 is 90, 80, 70. So I guess this would be 68 degrees. So 68 degrees and 22 should give you the same launch range. And then what launch angle leads to the farthest range? That would be your 45 degrees. Okay, so that's just reviewing. All right, here is an actual honest-to-goodness homework problem that I gave you. Let's see how it works. This is a little easier because you can cleanly split off the x direction and the y direction sorts of problems. So it says, a small ball rolls horizontally off the edge of a tabletop that is 1.2 meters high. Okay, so I'll draw the picture even though it's already sort of there. 1.2 meters high. It strikes the floor at a distance 1.52 meters horizontally from the table edge. Okay, so there's 2 meters. My ball comes off in this direction and immediately starts dropping. There it is. Okay, first it asks how long is the ball in the air, and then the second thing it asks is what is the speed at the instant it leaves the table. Okay, so there are two parts to this. Now, what I want you to notice about this is that the fact that the ball is initially going just horizontally actually cleans up this problem quite a bit. The reason it cleans up your problem quite a bit is that your initial velocity in the x direction is something or other. You don't know what it is. Your initial velocity in the y direction, however, is 0. That really cleans it up. So here's your y direction, here's your x direction. Let's make this our 0, 0. You could go ahead for part A and ask this just as a y direction problem. You don't need to think about the x. And you could go, for instance, y minus y naught equals 1/2 a t squared plus v naught t. The initial velocity in the y direction is 0. So that term goes away. The initial position in y is not 0. That would be 2 meters. Your final position in y is going to be right there, 0 meters. And your acceleration is our trusty old minus 9.8 meters per second squared. All right, so notice that this is quite a friendly equation. I just have minus 2 equals 1/2 times minus 9.8 meters per second squared times t squared. Solve it for t. Okay, so divide over that stuff onto the other side and then take the square root and you're done. Then on the other hand, part B asks, what is the speed at the instant the ball leaves the table? Now for this part, you need to realize that in the x direction, our ball is not accelerating. So our ball is simply going at the same speed the entire time. That means we can use our unaccelerated motion model. X equals the initial speed times the time plus the initial position. Well, this initial position in X is just going to be 0. The final position in X when the ball hits the floor is going to be 1.52 meters. The velocity I don't know, but the time I do know. How do I know it? Because I get it from part A. So use the time that you got in part A and then this other information to solve for V naught. And that gives you the speed. Okay, so in projectile problems where you start out with speed only in the y direction or the x direction, things get a lot easier. So that's the only example I'm going to do today. I've already been talking for quite a while. I think for Friday you should take a shot at trying to do all of the homework problems except for the last 3. The last 3 are the ones on circular motion, but try your best, see how far you get. I think you'll be able to do a lot of them, and bring a couple questions for Friday, and we can go over them then. So what have our big ideas of today been? All of those things that we developed in 1 dimension, like displacement, velocity, acceleration, those all convey directly to motion in 3 dimensions. Okay, projectile motion can be described by constant velocity in the x direction and in the and accelerated motion in the y direction. Why is it accelerating in the y but not the x? Well, because gravity is pulling down; it's not pulling side to side. And then finally, without air resistance, projectiles at complementary angles at, for instance, 60 and 30 or 70 and 20, they travel the same distance. Okay, so give your homework a shot and bring some questions for Friday. Good luck, and thanks for watching.